we described the results about how you translate, so to speak, translate an integral from one set of coordinates to another one. The general formula, well, for a double integral, for an integral over an area, is this equation in 1.89. So this is on page 32, the notes. So here we see an equation on the left-hand side, which is a double integral expressed in terms of the Cartesian coordinates, x and y. And in the setup to this equation, s and t were a new pair of coordinates for points in the plane. And the integral on the right is an integral which is an integral taken out with respect to the s and t coordinates. And the function f has been translated. So in the first argument for f, we now have the function of the variables s and t, which gives you x. And in the second argument, we have the function of s and t, which gives you y. So you translate the function f, you replace the differentials dx dy with, well, with ds dt, but then there is an extra factor as well. And this extra factor is needed to account for the different way in which the new variables s and t might measure area compared to the standard kind of uniform way that the variables x and y measure area. The point is that no matter where you are in the plane, a small change in x and a small change in y covers a certain area. So you have a little area element dx by dy, and no matter where the point in the plane is, the same size change dx and dy will still cover the same area with Cartesian coordinates. But with polar coordinates, for instance, it's very different. If you start off at the origin, a small change in the radius and a small change in the angle covers a certain area. So this is a dr d theta area. So I vary the radius a little bit from the origin and vary the angle a bit. And that covers a certain area. But if you're at a point far away from the origin, then the same change dr, and what angle have I got? I've got about a third of a quarter turn. Are you seeing that? Yeah. You see, this is the same d theta. The same d theta that I drew here, more or less. So this area element here is massively different than this area. The same angle is sweeping out a hugely different area, okay? If I sweep out an angle here with my hand is moving through a certain volume, say in 3 dimensions. But if my hand was 10 miles long and I swept out the same thing, my hand at the end of my 10-mile long arm would be sweeping out a massive volume. So it'd be traveling miles and miles and miles and miles and miles each time I moved my hand through the same angle. So the way, but that's different from how the Cartesian coordinates work. When you vary x and y a little bit, it always traces out the same area no matter where you are in the plane. Whereas polar coordinates, small changes in the variables, it depends where you are in the plane. Okay? So the area dr d theta changes as you move away from the origin. It grows as you move away from the origin. So when we're translating our integrals, because the integration is to do with summing up the contributions of the function f over certain areas, we need to take account of this change. And it's this Jacobian factor here, which is introduced, that's what does the job. Okay, so we defined, so this is the absolute value of the Jacobian determinant of the transformation from the coordinates xy to the coordinates s and t, which we defined a few lectures ago when we were talking about the chain rule in partial differentiation. Now, we talked through this example last time, but I'd like to do a few more examples. Do some triple integral examples. Everybody finished with that diagram yet? So a similar change of variable equation holds for these. If you want to do a triple integral over some region R, so you've got some region R which is now a subset of 3 dimensions. If you want to integrate some function x, y, z, dx, dy, dz, well, you can express this as a triple integral over the same region, but with respect to a new set of variables, say r, s, and t. And you replace x with its expression in terms of r, s, and t, y with its expression in terms of r, s, and t. Sugar. R, s, and t. Oh, this is crazy. But in here, you need the extra factor, which is the absolute value of the Jacobian of the transformation from your 3-dimensional Cartesian coordinates to this new coordinate system. So it's the absolute value of the Jacobian, which goes in there as an extra factor. Should have given myself some more room. So that's just the 3-dimensional version of that change of coordinate formula up there. So let's look at some examples using a couple of coordinate systems. So we're going to use 2 types of system. We'll use the new system's spherical polar coordinates, which is spherical coordinates, and cylindrical coordinates. So I'll remind you what those are. One of them is based on a sphere type, thinking in terms of spheres. The other one is based on thinking in terms of cylinders to describe points in 3 dimensions. So the picture for spherical polar coordinates is you've got your usual x, y, and z axis. But a point in space, how do we now describe it? We describe it by its radial distance r. This angle theta, which is the angle made by the projection of the radius down onto the xy plane with the positive z-axis, and this angle phi. I introduced this system a few weeks ago. That's the spherical system. The cylindrical system kind of has a similar diagram to it. So this system kind of locates the point as the point on a certain sphere with a certain radius and these 2 angles, theta and phi. Now we want to think of this point as lying on a certain cylinder. So the cylinder that this point lies on is this kind of cylinder here. And we define this cylinder as this thing here, which I'm calling rho. It's the Greek letter rho. It's like a radius, but it's not the actual radius. It's the radius projected down onto the xy plane. So we call it rho. Rho is the Greek equivalent of r, or r is the equivalent to the Greek rho, whatever. So we use rho, and we also use this angle theta, same angle over here. And then we also use the z coordinate itself, just the plain old z coordinate unchanged, which is the height of the point above the xy plane. So spherical coordinates and cylindrical coordinates. It's 1, 2. So this is diagram 1, diagram 2 for the cylindrical coordinates. So in order to, God, I hope I get this done. In order to do these examples, we'll need to know what the Jacobians are. So for spherical coordinates, we need to know the relationship between the three variables x, y, z and the three new coordinates r, theta, and phi. So you pick that up just by analyzing the triangles in diagram 1. The z coordinate is easiest to pick up. It's r cosine phi. And you look at the triangle involved with the angle phi and the hypotenuse r. The x and y coordinates are going to come from this triangle down here with the angle theta in the xy plane. And the hypotenuse there is r sine phi. So r sine phi is the hypotenuse, and then it's going to multiply cosine theta and sine theta to give you x and y. And the Jacobian I think I did this out before, didn't I? Or did I just do it in one of my tutorials? I think I just did it in one of my tutorials. Or did I do it in the lecture? Any questions anyway at this point? I see a few people. Everything okay? Yes, question. So for the x and y. So x and y are coming from this red triangle down in the plane. So it's a right angle triangle there featuring the angle theta. And what's the hypotenuse of that triangle? The hypotenuse of that is actually the same as this side up here, which comes from that right angle triangle up there. So the length of that, it's the length of the projected radius. And the length of that is r sine phi. So you get that from this triangle up here. So you're just kind of analyzing the two triangles, the vertical triangle involving the angle phi, and this horizontal, this flat triangle down in the plane involving the angle theta. So it's this length here, the hypotenuse there, which is r sine phi. And so it's the hypotenuse of this triangle down here. So it's hypotenuse times cosine theta and hypotenuse sine theta, which give you x and y. Because x and y are these two sides, are those two sides of that triangle down in the xy plane. Okay. Now, by definition, the Jacobian is a determinant. Dx dr, dx d theta, dx d phi, dy dr, dy d theta, dy d phi. Yeah, I'm remembering this now. I did do this example with my tutorial. So some of you, this may be a deja vu. So you got 9 partial derivatives to work out there. But you've got the formulae describing x, y, and z in terms of r, theta, and phi. So, you just simply whack down those partial derivatives. So we're differentiating with respect to r. So we see sine phi cosine theta. Dx d theta will be minus r sine phi sine theta. and dx d phi will be r cosine phi cosine theta. Doing the same thing to y, you're going to find sine phi sine theta. dy d theta is going to be r sine phi cosine theta. And dy d phi is going to be r cosine phi sine theta. dz dr is cosine phi. dz d theta is 0, thank you, speeding me up. And dz d phi is minus r sine phi. Yeah, okay. So you got a 3 by 3 determinant, so your heart sinks at this point. Think, oh my God, I got to do all this. But approach it carefully. Employ or try to exploit the properties of determinants. So the key property of determinant is when you factor any row or column, when you extract a common factor out of any row or any column, you can take that factor out, and then it comes outside the determinant. So in particular, there's an r sine phi. R sine phi is a common factor of the middle column. And indeed, there's a second factor of r. R is a common factor of the third column. So I can extract out in total an r squared sine phi. Take the r out of the third column and take the r sine phi out of the middle column. So I get r squared sine phi. And then I've got the simpler determinant to do. So I'm just left with minus sine theta, cosine theta 0, and cosine phi cosine theta, cosine phi sine theta. And what's left there? Sine phi. Okay, well, that's a lot better. That's a hell of a lot better. Are there any more common factors? Maybe, maybe. No, there isn't. Okay. But we do have a 0 here, so we should definitely expand it through that 0, either along the third row or down the middle column. Let's go along the third row. So I'm going to have cosine phi into the 2 by 2 determinant. Now the 2 by 2 determinant, it becomes minus sine squared theta times cosine phi minus cosine squared theta cosine phi. Then you've got a 0 here, so you don't need the cofactor. Sorry, question? Yes, because I took out the r. Thank you. Thank you very much. So we don't need n for that. And then we come to this one. So that's crucial, obviously. Then I have minus sine phi times the 2 by 2 determinant up here, which is going to be cosine squared theta sine phi plus sine squared theta sine phi. And what happens here? Well, in both of these inner brackets in here, you've got your sine squared plus cosine squared. So you have cosine of phi, and this is just minus cosine of phi in there. Then you have minus sine phi, and in this bracket in here, it's just sine phi. So in fact, we just get minus r squared sine phi. So I've got two a few applications there of this result that sine squared plus cosine squared equals 1. Sine squared of anything plus cosine squared of the same thing equals 1. It's got 2 applications of that here. So this is the value of the Jacobian minus r squared sine phi. So it's the absolute value of that which is going to go in to any examples we use with looking at triple integrals. So we can do the same thing for the cylindrical coordinates. Well, what are the, I haven't written them down yet, what are the functions defining the relationship between the coordinates? Well, you look at the diagram for cylindrical coordinates. There it is, and the relationship between x and y and rho and theta just simply comes from this triangle down here, this right angle triangle down here involving the angle theta. And z, well, this is just the same z coordinate. So this kind of throws people sometimes, but you know, your third transformation equation is just z equals z. It's the same coordinate being used in both systems. You've got rho cosine theta and rho sine theta giving you your x and y. So things are simpler here, so the Jacobian comes out easier. So it's the same initial definition for the Jacobian, this matrix of partial derivatives. I won't bother writing that specification out again. Just do it. So we're doing dx d rho is cosine theta, dx d theta, so we got minus rho sine theta. And dx dz, well, there is no z in x, so derivative is 0. dy d rho is sine theta. dy d theta is rho cosine theta. dy dz, 0. So there ain't no z there. Then these ones, we have all the partial derivatives of z. Well, there is no rho in z, there is no theta in z, and z is z, so dz is just 1. So it's a much simpler determinant that comes out when you're looking at cylindrical coordinates, and you can just expand that directly. It's just going to be equal to this 2 by 2 determinant up here. And that's going to be rho into cosine squared theta plus sine squared theta. So in other words, it's just rho. So that's a lot tidier. Okay. So, okay. Any yeah, question? It tells you that they measure area differently. It tells you that the area that a small change in the cylindrical coordinates, rho, theta, and z, if you make small changes in those, the volume of three-dimensional space that they trace out increases as a multiple of the coordinate rho. So it does depend how far you are from the origin. As you get further and further out from the origin, the volume of space traced out by a fixed small change in the cylindrical coordinates, it grows like rho. It doesn't matter how high you are. It just depends on your distance, your projected distance of the xy plane away from the origin. Whereas because the Jacobian for the spherical coordinates depends on the square of the radius and the sine of the angle phi, so it's telling you those two factors. In there, it's much more, I mean, the major factor is the r squared. That's the one that's going to grow very large when you get far away from the origin. The sine phi just varies between 0 and 1. Okay. And it affects how the integrals transform into those coordinate systems, because these are, when you're transforming the integrals now, you're replacing dx, dy, dz with the corresponding Jacobian and then the three differentials for the new coordinate system. So let's have a look at some actual example integrals. Everybody got that page? So those are the two coordinate systems and their Jacobians. So for this first example, we're going to consider a circle of radius 3 on the xy plane. And this point up here, which will be at a height 9. And we're going to consider this kind of shape here. So we're going to consider this region R, which is a subset of three-dimensional space. And it's going to be bounded by, now this is a paraboloid, R squared equals 9 minus Z. So R is giving, so we're going to talk about rho. So make that rho squared. We're talking about the cylindrical coordinate system here. So this surface here, this kind of curved bell-shaped surface, at height z, it's got a circular circumference or circular cross-section with whose square of the radius, whose radius squared is 9 minus the height z. So it's bounded by this, and it's cut off at the bottom by the xy plane. And by the plane z equals 0. So it's the volume of three-dimensional space contained in this kind of bell-shaped kind of thing, bell-shaped paraboloid. So we want to compute the integral, which is a triple integral over R of the function rho squared dx, dy, dz. Or you could have even written that purely in terms of Cartesian coordinates. It's the integral of x squared plus y squared, yeah, dx, dy, dz. Well, so the first point is to recognize that the Cartesian coordinates are very bad, or a poor fit to this problem, because the problem has a definite circular aspect, because the cross sections of this shape are all circles. And secondly, the radius of these circles is changing in a very prescribed way according to the height. So it looks very cylindrical. It looks like it'll be much easier to describe this in terms of cylindrical coordinates. Okay, so we'll convert to cylindricals. So this integral I is now going to be the triple integral over R of rho squared times the Jacobian for the cylindricals, and the Jacobian was rho, wasn't it? So we get another rho, d rho, d theta, dz. So now we'll start putting in limits. We got a rho cubed, d rho, d theta, dz. Now, you remember I described to you the way to do this is to work from the outside in. So you look at your region, and you first look at the z variable, and you say, well, between what values of z do I need to cover? I should put this on that screen as well. Between what values of z do I need to cover in order to oh my God, that was the left. Sorry, just make it easier. Yeah. Between what values of z do you have to go in order to capture the region? Well, you need to go from z equals 0 up to z equals 9. Okay, that's where there's no more bits of the region beyond z equals 9. What values of theta do you have to take into account? Remember, theta is this angle here. Well, sorry, question. Because, so why did the extra rho come in? Because I'm following this formula. I have the Jacobian and then the differentials for the new variables. Yeah. So you can think, another way of thinking of it is dx, dy, dz is equal to rho, d rho, d theta, dz. You need the extra factor of the Jacobian in there. What kind of angles theta do you need to do? Well, this volume is all around the z-axis. So I need to go the full range of theta between 0 and 2 pi. And finally, what values of the rho variable? Well, the rho variable is kind of like the horizontal radius, so the radius of the cross-section. So I always need to begin this radial term at 0. And according to the setup, at height z, you see, remember, the outer integral is z. So z is providing a value to this inner integral here. So I always go up to the upper limit 9 minus z on the radius. So that looks like we've successfully translated it across into cylindrical coordinates. And it's all set to just kind of weigh at it and do the evaluation. So you can leave the outer two integrals alone for the moment and just perform the inner integral. So it's a rho 4 over 4. And it's 9 minus z over 0. So what's that? So that's just integral 0 to 9, 0 to 2 pi. We just got 9 minus z to the power 4. d theta dz. Well, what's going to happen here? Now we have to integrate that with respect to theta. But look, it doesn't have a theta in it. So it's just going to act as if it were a constant with respect to theta. So you're just going to pick up a multiple 2 theta times this integral now. Yes, thank you. Or indeed, I could have shut the 4 out to the front as well. And can I integrate this without expanding it? Yeah, I should be able to do that. So you got a pi over 2. And that's going to integrate to 9 minus z to the power 5 over 5. But it's going to have a minus sign attached to it because because it's a minus z on the inside, so you have to do kind of integration by substitution there. And then you have the limit 0 and 9. But of course, when you put in the upper limit z equals 9, it's just a 0, isn't it? So and when you put in the lower limit z, you get 9, and you're subtracting it. So it seems to be just 9 to the power of 5 over 5. So 9 to the power of 5 over 10 pi. Which is whatever it is. Okay. So like the hard thing there was doing the translation. Getting it successfully to this stage. We've still got time to start another example. I hope I did everything okay there. I think I did. Yeah. So how did I do that? So what happened? So I got it to here, and I said I won't bother expanding out the polynomial. I just leave it as that. But look, I have to integrate it with respect to theta. But there is no theta there. So I'm just integrating a constant with respect to theta. So that's just going to integrate to that constant, which is this thingy, 9 minus z to the power 4 over 4, that constant multiplied by theta, which then evaluates at 2 pi and 0. So it's just going to evaluate to 2 pi multiplied by that constant. So I'm using there the fact that if you integrate 0 to 2 pi, any constant k d theta, you just get 2 pi k. Well, because I put the 4 out as well. Yeah. Didn't I? 2 over 4. That's for a constant k. And this thing, 9 minus z to the power 4 over 4, that is a constant as far as the integral theta is concerned, as far as the variable theta is concerned. Is that okay? Any other clarifications? So the next example, which will be one using the spherical coordinates, and maybe just got time to define this. Find the mass of a sphere with radius a So to characterize the sphere, you just have to say what the radius of the sphere is. But this sphere is made of a funny material. It's made of a funny material which changes its density depending on the distance from the origin. So find the mass of a sphere with radius a whose density is proportional or inversely proportional to the square of the distance from the sphere center. So as you move away from the center of the sphere, the material becomes less dense. Okay, i.e. the density the density could be written as some function like this for some constant k. So the principle we're using here is that the mass is just the sum of the density across the whole object. You're just summing up the density of the object at every point. So you're integrating the density function across the whole sphere. Well, how do you do that? Well, you certainly don't do it in Cartesian coordinates because they're very unspherical. They're fine for describing rectangular stuff or boxy stuff, but not so great for curvy stuff. The function now is much easier to describe, the density function. It's k over r squared. The Jacobian, what was it? R squared. And you use the absolute value of the Jacobian. So the minus sign in front of the Jacobian doesn't really have any meaning. We have r squared sine phi dr d theta d phi. And what are the limits for a sphere? Well, here's, there's the roundy sphere here. It's the angle phi, it's the angle theta. Well, d phi, so we normally think of this angle phi as going from, so this is the angle off the positive z-axis. So we'll go from 0 to pi there. So that will take us from the positive z-axis all the way down to the negative z-axis. So varying pi like that traces out this kind of half cross-section of the sphere. But then I want to spin that all the way around. So I want to go 0 to 2 pi for the theta variable. And then the radius, well, the radius goes from 0 to a because the sphere's radius a. So you can see a bit of simplification here anyway for integrating this. The r squared terms are going to cancel. So I've just got k sine phi dr d theta d phi. K is some constant, just this proportional constant for the density. So the k can shoot all the way out to the front. And then indeed, there's no r or theta here anymore. So actually, the k is going to go all the way out to the front. The theta integral will just give you 2 pi. The r integral will just give you a, and you'll just be left with the phi integral, 0 to pi of sine of phi, d phi. So I'm shooting things around in there due to the fact that there's no r or theta in the integrand. So the integrating with respect to r and with respect to theta just gives me the length of those intervals, so to speak. So I better finish up real quick. Integrate that, that integrates to minus cosine phi, evaluated at pi and 0. What was that? Is that a 2 or something? It's minus 1, minus 1. So it's minus. Yeah, but it's minus, so I think it gives you a 2, doesn't it? 2. So it gives you 4. So it's 4k pi a. So that's what the mass of such a sphere would be. 4 times whatever this proportional constant k is, times pi times the radius of the sphere. Okay, I better leave it there. Give you a break for the next hour.